Hi. So in the previous video, we learned about the dot product of two vectors and learned also about the properties of the dot product. Now it turns out that there are a couple of quantities in physics that would need another formulation to calculate these quantities, and the dot product would not be enough for that. Okay, as an example, when we think about the angular motion. So, for example, the torque required to cause some angular acceleration if you have like a particle, and then this is like, for example, our coordinate. This particle is at this position R, and then this particle has some velocity v, and accordingly then it has a linear momentum of mv. Yeah, so m being the mass of this little particle. Yeah. Now imagine this would be the p vector being the linear momentum, linear momentum of the particle. Now, how could we, for example, calculate the angular momentum of this particle? Now, it turns out that the angular momentum, we would show that by L, for example. This vector would not be in this plane of R and P. However, it would be perpendicular to this plane, and we could calculate that from these two vectors of R being the distance to the axis of rotation, for example, and P the momentum, the linear momentum. Now, let's say these two vectors, if I move this R to here, if these two vectors have an angle of theta with each other, now it turns out that we can write this L being the angular momentum as the R, something we call cross P. Yeah, and what this cross product is, I will explain later. So this would be one example. Or the other example is that if we have, for example, a charged particle, let's say we have a particle that has a charge of Q, and then we put this particle in a magnetic field. Let's say here we have a magnetic field B, and this particle also moves in this field with some velocity v. Then we want to calculate the force that is applied on this particle from the magnetic field, or the force that this particle would feel. That also turns out that this force from the magnetic field, let's call it F of m, this force would also be perpendicular to the plane that the vector v and the vector b would make together. And this is not necessarily, as you see here, in parallel. It could be like the v is like this. So the particle with velocity v and a charge q is moving in this direction, and here is our magnetic field, and these two vectors make some angle together. Yeah, and then the force applied on the particle would be perpendicular to this plane. Yeah, so then one could write this as q v, the vector v cross B being the magnetic field. So this is the reason that we also should cover what cross product of vectors is and why it is very useful. So as opposed to the dot product, so we discussed the dot product before. The dot product gives us a scalar. However, this cross product of two vectors gives us a vector. So this being a main difference here. And so let's say we have now two vectors, one vector A and the other one vector B, and let's imagine that these two vectors make an angle of theta with each other. Now we define vector C as the cross product of A and B, and this is the notation for a cross product, yeah. And this would be the magnitude of A times magnitude of B, and the sine of theta, this theta being the angle between the two vectors. And obviously, since I need it, so far this is only a scalar, but we said C is also a vector, so now we need also a vector here. And this would be, let's say, a unity vector, and the direction would be certainly perpendicular to the plane of these two vectors. So let's say, for example, if these two are making this plane together, then the C vector would be always perpendicular. You should imagine this in 3D to them. But it could be in this direction, or it could also be in this direction. And that also depends on the order of multiplication here. So, for example, we could already write the first property of the cross product, that the A cross B is not equal to B cross A. However, it is minus B cross A. And this is the property of anti-commutation. Yeah. And we see already here also the difference as opposed to the dot product, where if you remember, we said the A dot B is equal to B dot A in the dot product, and that means the dot product has the property of commutation. Yeah. So it's just a reminder, but what we are talking about now is the cross product. So if you are calculating the cross product of A times B, it could be that you will get, for example, the C, but the B cross A would be in the other direction with a negative sign. But similar to the previous case, the cross product also obeys the rules for the distribution. Yeah. So, for example, if we have A cross B plus C, yeah. So here we can distribute the cross product and get A cross B plus A cross C. So the cross product is also distributive. Or another thing, it's also associative. So for example, if we have kappa being a scalar, yeah, times A cross B, we could also write this as kappa A cross B, or A cross kappa B. these things are all equal. The only thing that we should never do is that we are not allowed to change the order of A and B here, here, or here and here. Otherwise, we should have a negative sign included. Okay, so here we explained how we calculate the cross product with a geometrical notation of, for example, the sign between the two. However, I would like to also calculate this cross product in terms of the, components of the vectors. So how do we do that? Let's say we have vector C, which is A cross B. Yeah, and let's make a quick sketch of Cartesian coordinate x, y, z, and I remind here our unity vectors of ex, ey, and ez. And I mean, we could also talk about I, j, k again, but since I want to extend this notation to higher dimensions or to coordinates other than Cartesian, which are not necessarily, for example, perpendicular to each other, then from now on I want to work with the notation of E hat when I talk about the unity vectors, okay? Now, so we have to now sketch our two vectors, A and B. There can be anything, but let's say this is my A, and this is my B vector. So just a generalized case. Now, I would like to write this vector C in terms of the components of A and B. So how do we do that? Let's see. This is our C vector. So A, what is A? We said this before. It is AX, EX, plus AY, EY. Yeah, so a linear combination of the components plus AZ, EZ. So this is our A vector. Now we have the cross product to BX, EX plus BY, EY plus BZ, EZ. Yep. Now, what we can do, because we learned that the cross product is associative, yeah, and distributive. So that means we can take one of these and then multiply it to all of these and then plus the next one and the next one. Yeah? So we can simplify it. The only thing we are keeping in mind here is that these three vectors are perpendicular to each other. And so maybe we could quickly write first the properties of the unity vector here, and then we can continue easier. So how do we calculate EX cross EX? So imagine what would be the cross product of a unity vector of EX times with itself. I argue that this is 0, and the reason is that this would be, the magnitude of EX times the sinus of the angle between them. So it will be magnitude of EX, and the sine of theta, and this, what is the angle of a vector with itself. This is 0 and the sign of 0 is 0. Yeah, so this would be 0. Okay, so I don't have much space, so I delete this here. And with the same argument, so EY cross EY is also equal to EZ cross EZ, and this is 0. And also, if we want to calculate the this time EX, and now if we want to calculate, for example, EX cross EY, what do we get? This would be EZ, yeah? It would be a vector perpendicular to the plane of X and Y, meaning in the direction of Z, and with also the unity magnitude. Yeah? And so already here we can imagine if we have EY cross EX, this would give us minus EZ. Yeah, so the C and minus C, as we explained before. And so we can have the same type of calculation for all of these unity vectors. Have our little formulas here we can use when we distribute these two parentheses and cross product them. But I write a few components, and then the rest would be trivial, I guess. So for example, if I start from here, so this one, and then I distribute it to the others, the first two, this would be AX, BX, and then EX, cross product EX. And this, and then plus the rest of the components. And this we already know it is 0. Yeah, from here we learned that this is 0. And then the next one would be this part, cross product to this one. And what would that be? That would be AX, BY, and then the cross product of EX and EY, which we already know it is EZ. Yeah, so I just write it directly EZ hat. Yeah, and then we continue with the rest of the multiplications. So it would be obviously now this time multiply this, then plus this one times all of them, and then this one times all of them. And so now I just keep the time and leave this to you. And so we can already summarize what we have at the end. So I could write this as AX BY minus AY BX, and this multiplied EX cross EY plus AX BZ minus AZ BX, this times EX EZ, and I still have one more, so that's plus AY BZ minus AZ BY times EY cross product EZ. And now it's time we can use our little calculations here and use it on top of this. Like for example, this will give me an EZ, or similar for the other ones. So I can now summarize it and write that is equal to AX BY minus AY BX. So what is this? This is EX cross product EY. This gives me EZ. Yeah. And then the next sentence would be AX BZ minus AZ BX. And be careful here, EX times EZ gives me minus EY. And the last one is AY BZ minus AZ BY. And then EY EZ gives me EX. Yeah. So, what did we do? We calculated vector C, which is A cross B. We opened up A and B vectors in terms of their components and calculated the whole multiplication component by component. Yeah. Now I ended up with let's use pink, with three components, this, and this. And remember, we're calculating vector C. So actually C could also be written as CX, EX, CY, EY plus CZ, EZ. And now if we compare this to this, we can already write what are each components of C. So for example, CX times EX, that gives me here that CX should be this parenthesis. So CX should be AYBZ minus AZBY. Yeah. So that means this parenthesis is my CX, and this parenthesis is my CZ. Yeah. And this one obviously is CY. So I write this once more. Once the components of our C vector, Cx, Cy, and Cz. So that means now we have, if we have the vectors A and B and its components, we can easily this way calculate the components of vector C, being the cross product of A and B. Now, there is a nice way or another notation to write this, which physicists love to use this notation, and that is using the something called the Levi-Civita symbol. Yep. So I introduced the Levi-Civita symbol, and usually we show that with a sign of epsilon, I, J, K, and this would have a value of 0 if two of these three ijk's are equal. Like, for example, if I or j equals k, or k equals I, and so, yeah. And then this will give me a value of 1 if I, j, k make an even permutation. And I tell you what I mean there. Permutation, and -1 if we have an odd permutation. Or maybe it's better to write this also as if I or j or k are same. If they are the same, then we get 0. So what do we mean by this permutations? Like, for example, imagine if we have I, j, k as numbers, for example 1, 2, 3, then an even permutation would be 1, 2, 3, or 2, 3, 1, or 3, 1, 2. Yeah. So one way I write it for myself, always to remember, is like this. If you go 1, 2, 3, and so you go to 1, 2, 3, this is an even permutation. Or you go to 2, 3, 1, same. Or 3, 1, 2, same. So I write here, this would be these 3 are even permutations. And if I want to also mention the odd permutations would be counterclockwise. So for example, here if I say 3, 2, 1, yeah, 3, 2, 1. So I start from 3 and then go counterclockwise, 3, 2, 1. Or I say 2, 1, 3, or 1, 3, 2. So these are called the odd permutations. And so what is this Levi-Civita symbol? Basically, it's saying that if you have this epsilon with this I, j, k, and if you have any of these two the same, so for example, you can already tell me the epsilon of 1, 1, 2 is 0. Why? Because 1, 1, I, and j are equal. Or anything else, 2, 2, or 3, 3. Any of these indices that are similar, then the epsilon is automatically 0. Yeah? And about the permutations, I said you can write this little diagram here, 1, 2, 3, and then if it is counterclockwise, it's an even permutation, it is 1, and if it's the other way around, it is -1. And it turns out that this Levi-Civita notation helps us a lot in simplifying this cross product. So one way of simplifying this is to write that C of I equals the summation over J and K, epsilon I j k being the Levi-Civita symbol, times A of J and B of K. So writing this little formula would be equivalent to all these calculations that I did, and I could derive the C. I could write it also as this formula. Another handy way of calculating the cross product of C A cross B is to use the determinant. So it's actually very easy. So you can write C being and yeah, the C would be the determinant of EX, EY, EZ. So these are vectors, yeah. And then of A and B, you write A and B on each row. So here I have the AX, A, Y, A, Z, and BX, BY, and BZ. And if you calculate this, you get the same result as we calculated before. I don't want to go too much into the calculation and the properties of determinants. This we will cover later. But for now, just know that if you want to calculate the cross product, you could also easily write this kind of determinant and vectors. And if you calculate this determinant, then you can easily calculate the C vector.